Alright, today's lesson we are going to cover exponential and logarithmic graphing. But before doing so, we are going to, before jumping into transformations, we are going to basically look at the parent functions and look at the certain characteristics that they each have in order to better understand how to do transformations. So, first of all, we're going to look at exponential function. Each positive real number base produces its own parent function, so there's no true parent function. Here below are some most common exponential functions. I prepared the calculator here to kind of give you an idea what they look like as we graph it right off the bat. So 2 to the x, e to the x, and 10 to the x. So you notice that these bases are constantly increasing. So when I hit graph here, here's the 2 to the x power, exponential growth, 2.72 to the x power, which is our e. Notice how much faster it's increasing, and then 10 to the x, it tends to shoot or rise up a lot faster than the other two. Okay. So anyway, here they all are. But anything to the 0 power, 10 to the 0, 2 to the 0, or e to the 0 is a 1. Therefore, notice when x is 0, they are all intersecting here at y equals 1. That's their y-intercept. So if we look at these graphs, notice that they're continuous graphs from left to right. There aren't any graphs, they're smooth graphs. Basically, if you were to take your pencil and trace them, you would never lift your pencil off the paper. So we can easily go ahead and say that the domain of these graphs is going to be all real numbers. Whether you choose to write it in interval notation or domain, interval notation, or if you decide to just use the symbol all real numbers, either one's acceptable. When it comes to the range are the y values that are being used. If you notice as well, all three of these graphs were above the y equals 0 line. They never fell below that line. So they were all positive y values. So the range in this case, you can say 0 to infinity, or which most of you guys prefer doing is y greater than 0. Now I do want you to notice that I am not putting an equal to this inequality, because these graphs get very, very, very close to this x-axis, but they never really do cross. And the reason so is because this is considered a horizontal asymptote. So horizontal asymptote. And the equation for a horizontal asymptote, that is the x-axis, would be y equals to 0. So every single one of those graphs get awfully close to the x-axis but never do intersect the x-axis. So that's the domain and the range. When we do asymptotes, we will use a dashed line to depict them. Since this one is actually sitting on the x-axis, it's kind of hard to draw a dashed line upon a solid line, so it's understood to be there. Okay, now let's look over here at the log function. Now these functions are inverses of one another. Okay. These are inverses of one another. So in essence, if we were to draw a y equals x line, okay, the graph of the exponential function reflected over the y equal x line would result in this one. And just to give you a visualization here, let me kind of draw one here just to give you an idea of what I'm talking about. Okay. So there's our y equals x line. If you can picture one of these graphs being flipped over onto this side, notice that this is what you would end up with. Okay, your graphs would go, increase, and then increase, rise up, increase from the left. Okay, so whenever you reflect a graph over the y equals x line, you get what we call the inverse, and that's what you're getting with the log functions over here. So let's talk about domain and range with this graph. Well, the domain values are the x values that are used to graph these. Well, here's our x-axis, and if you notice here, no graphs are occurring to the left of this ruler. Everything is occurring to the right of x equals 0. So the domain is going to be x greater than 0. Notice that that was switched now to the domain. Okay? They interchange these values. Look at the range. The range, what y values are being used. Well, this graph is going to go all the way down, and it goes all the way forever increasing. So y values end up being all real numbers for this graph. Again, pointing this out. For exponential function, the domain was all real numbers. Therefore, the inverse means that the domain values of this function become the range values of this function if they're inverses. Same idea here. If the range is y greater than 0, whatever the range is becomes the domain values, and because domain has to do with x, we switch that y to an x. Okay, works vice versa. And you can also reflect it here if you want to look at it this way too. Let's draw the y equals x line right here. If I kept drawing it here. If I reflected this time going from here and flipping it to this side, you would end up with this graph. So it goes back and forth. Okay? So there's your domain domain values, and these are your range values. If this has a horizontal asymptote, well, what's going to happen on this side? Well, yep, you guessed it, vertical asymptote. Okay? And this time the vertical asymptote, instead of saying y equals to 0 like this one, well, the y changes to an x. It's going to be x equals 0. So I'm just going to put here an arrow, and let me write here x equals 0, so that you recognize that there is a dashed line going up and down against the y-axis. Therefore, it's x equals 0. Okay? So horizontal asymptote, I'm going to put here for your notes, is the x-axis. Vertical asymptote is the y-axis when it comes to logarithms. Okay? So let's look at these transformations. What I want you to do on your own is the following. So if you have a graphing calculator, do the following. We are going to compare these new graphs to the original parent function f of x equals to 2 to the x. So what I'm going to do is I'm going to go back to my graphing calculator, and I'm going to erase the other two values that I had here. So I'm going to delete this one, and I'm going to delete this one. Let me delete it completely. And whichever function I'm comparing to, I'm going to put it in here. So the g of x is 2 to the negative x. So I'm comparing it to my parent function 2 to the x. So 2 to the power of negative x. Now I'm going to graph. What I'm going to notice is that the first graph that graphs, that's the 2 to the x power. And the second one that graphed, well, something happened. Well, we notice that this graph flipped over like that. Okay? And this is considered our y-axis, so there's a reflection happening. So for our transformation, you're going to write, well, it reflected over the y-axis. Okay, now we're going to do it again. This time, it's negative 2 to the x power. So I'm going to come back over here, go to my y equals, and I'm going to put negative 2 to the x power. So I'm going to clear negative 2 raised to the x power. Now I'm actually going to do something over here just to make a difference. Over here in the front of y1, I'm going to hit enter to make my graph a little bit easier to differentiate. Okay, so the thicker one is 2 to the x power. So here's that first one. And the next one, the transformed one, well, look what it did. So now it went from up here and it flipped downwards that way. So it flipped over this x-axis. So let's write that over here. Reflected over the x-axis. So I want you to pause the video and I want you to do what we did over here and fill out the rest of these spaces and then unpause to check your work. Okay, so at this point you are checking your answers. So notice that when you're adding or subtracting against the x values of a function, you are moving horizontally and you will always do the opposite. So the -3, which is really hard to see, I apologize about that. The minus implies right, the plus you go left. And then when you are adding or subtracting against the entire parent function, okay, so the parent function is 2 to the x, so we are adding or subtracting to the entire parent function. That means vertical movement is occurring, and you always do exactly what the sign says. So the +2 implied up 2, the -3 down 3 for vertical. And then when it comes to the last ones, when you have your parent function being multiplied by a coefficient, that is going to affect the graph by either vertically stretching or vertically compressing. So what I want you to do is look at the coefficient, and if the coefficient is, I'm going to use C, greater than 1, you will have always a stretch factor. If the coefficient falls between 0 and 1, as this one did, the 1/2, you will have a vertical compression. Okay? So instead of having you waste your time, it's not a waste, but it's going to be kind of redundant. Instead of having you do all of this all over again, I do want you to recognize that this is going to be the same thing that happens here. Okay? Multiplying the x by negative will always be a reflection over the y-axis. Multiplying the entire function by negative causes a reflection over the x-axis. This applies to all functions, not just exponential and logarithm, but all functions, okay? Whatever is happening to the x value is horizontal movements. If you add or subtract to the entire parent function is vertical movement. And then again, you have your coefficients again. Here, there was coefficient of 4, vertical stretch, coefficient less than 1 and greater than 0, therefore vertical compression, okay? So, see other table is what I'm going to write, okay? Same thing happens all over again. So let's talk about how we are going to graph these, especially for our test that's coming up. I'm going to have you guys use your calculator to construct those tables, okay? But let's talk about the transformation first. So the parent function in this problem has to be what? Here is the equation right now. R of x equals 2 times e to the x minus 4 plus 1. So it's an exponential function. So I look for my base, and my base is e. So my original parent function for this case would have been e to the x power. Okay, so it went from this to this. So notice that the new things that were added onto it were these things right here. Okay, so those three characteristics or three numbers have influenced the f of x equals e to the x graph somehow. Well, how? Well, let's go left to right. This 2. That 2 is a coefficient. It's greater than 1. So we are going to have a vertical stretch by a factor of 2. Then the next number was this minus 4. Well, this 4 is subtracting from x. X implies horizontal movement. We do the opposite. So 4 units to the right is what it shifted. And then lastly, the plus 1 is adding to the entire function. So it went up 1 unit because we do exactly what it says to do. As far as our table, those are just your choices of what you're going to choose. So I'm going to erase this, what we have, and I'm going to enter the function that we have. So 2, let me go back up here, 2 to the e. By the way, if you're looking to know where e is right here, right above ln. So it's in blue. Okay? So 2 to the e x minus 4. And I'm going to arrow out to get out of that, and then it's plus 1. Okay, so I'm going to graph it, so I'll have an idea of what I'm expecting. Notice the shape does not change. It's still an exponential growth problem. Alright, so there's our growth problem, so that's what it looks like. Right above graph, you'll see the word table. It's in blue. So I'm going to do second table, and bring up the table. And I'm going to pick some x values. I'm going to go back and start over here with the negatives. So -4, -3, let's start with -2, okay? So -2 is 1.005. So I'm going to come over here, I'm going to write -2, and this is 1.005. And then the next one we had was, let's see, all these are kind of close to 1s. Let's go a little bit higher than 1. So let's go +2 is 1.27, so close to 1.3. So let's go to +2, and it was 1.271. 1.271. All right, let's keep scrolling. All right, oh, here, this one jumped up a little bit. I don't know. Let's see how high this goes. Oh, it goes all the way 15. Yeah, let's take advantage and let's use 3. 3 is 1.7357, so let's put 3, 1.736, what is it? Yeah, 736. And then we knew 4 is going to be a 3, and then we had 5 is 6.437. 5 is 6.437. Okay? So we're going to graph these, and so our x values go from -2 to 5. I have enough space on the x-axis, and here we're going 1 to 6. So I could probably count, let's see, 1, no I can't, 2, 3, 4, no I can't count by 0.5, so we'll just count by 1 on everything. So -2 is a 1.005, so let me do that. So here's -2, 1, and a little bit above 1. Okay. 2 is 1.27, so around 1.3. So I'm going to go 1, 2, and go 1.3, just a little bit higher. And then 3 is 1.7, so 3 is almost at the 2, but not quite. So around right there. 4 is a 3. 1, 2, 3, 4. 1, 2, 3. So I'm starting to see the shape develop. 5, 6.4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6.4. So a little bit less than 6.5. Okay, so I can see right away that there's my graph developing, right? And if you needed another point, I mean, goodness, add another point. I mean, if we wanted to go back to some more negative numbers, notice, whoops, I need to go over here to do that. I go scroll up. The further I go, see -7, -8, it's actually saying 1, but it's not really, and I'll show you why. But -6 is still just above 1, so all of these are just, it's going to flatten out. So why do you think that's happening? Okay, so let's go ahead and talk about that. Now it's saying it's 1. It really isn't 1, but it's constantly saying that. And the reason why is, hopefully you're recognizing it, is that we have to deal with horizontal asymptotes when it comes to our exponential graphs. Recall here that our graph was at y equals 0, okay, and it did what? Well, the whole graph went up 1 unit. Remember what I said down here? So not only does that curve and all its points go up 1 unit, but it has some company in the asymptotes. The asymptote must also join in the movement. So the y equals 0 was originally right here, okay? And due to vertical movement, it went up 1. So we need to acknowledge that by drawing a dashed line. So let me do that right over here. So let me do that, and then I'll get my hand out of the way. So there is my dashed line. That is my horizontal axis. And the reason that's important is because when I draw this graph over here, my graph has to get awfully close to the horizontal axis, but it doesn't ever touch it. So I'm going to do a little bit of sketching here to get my curve. Whoops. Needs to curve up a little bit faster. There we go. Show my arrows. And then this flattens out. So let's flatten it out over here a little bit. I'll use the ruler to help me draw this. Okay, so that I can see that it's not going to touch the x-axis. The y equals 1 axis very much. So I'm going to zoom in here so you can see. So notice I'm getting really, really awfully close, but I'm not going to cross that axis. So now my horizontal asymptote is no longer at y equals 0. It moved up 1, so it's at y equals 1. Okay? So let's zoom out here. So at the bottom, let's go ahead and fill out the characteristics of domain, range, and asymptote. Okay, I'm going to straighten this out a little bit more. So the domain values did not change. It's still a smooth graph from left to right, continuous. All the x values are being used. The range now is not y greater than 0. It moved up 1. It's now going to be y greater than 1 because all the y values are above the horizontal asymptote. And we already discussed above what the horizontal asymptote is. It's y equals 1. So I need you to mimic what you just did here, and I want you to work out the horizontal asymptote, not the horizontal asymptote. I want you to work out the logarithmic problem over here. Do the same thing. Give me the transformations, fill out the table, and graph it. Pause now and check with me in a bit to verify if your transformations came out right. Okay, so check your transformations. Did you get a vertical compression of 4/5? Compression because it was a coefficient between 0 and 1. Did you say left 3 units because you do the opposite and it's adding it to the x? And then the -2 is subtracting by the entire function. That means vertical movement, and you do exactly what it says. Negative means go down. Hopefully that's the case. And as usual, you are comparing it to the parent function of h of x equals ln x. Okay, so pause again now. Fill out your table and graph. And don't forget to graph your asymptote, okay? There's also an asymptote on this one. And then check back with me after you've done it on your own. Okay, so let's graph these and see in comparison what it was to yours. Again, you do not have to have chosen the ones I chose. It doesn't matter. Ultimately, our curves are going to look alike. I've decided that my y-scale, I'm not going to count by ones. I'm going to count each line as 0.2 to facilitate my graphing of points. So let's see, -2, -2. So I'm going to go -1, -2. Then there's going to be 0.2, 0.4, 0.6, 0.8, -1. Then 2, 4, 6, 8, -2. So this one's going to come way down here, kind of almost off my page. Then -1, and I have to go -1.45, which is around -1.5. So 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, so 1.5 negative is around right here. Okay. This graph paper didn't get on, was not dark enough, so it's very annoying. Alright, 0. So negative 1.12. So 2, 4, 6, 8, 10 for 1. And then this is going to be 1.2, so 1.1 has to be somewhere in the middle. So I can start seeing the curve is going like that. 3, 1, 2, 3. And I have to go to 0.6 approximately. If you round up that. So 3, 0.2, 0.4, 0.6. So just about 0.6. Okay. And then 7. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. And 0.16, which is close to 0.2. So a dot right here. Because the line here is 0.2, so this is 0.16 around here. Okay, so I can see this is what's happening to my graph. But before graphing that, I always tell students, please don't draw the curve until you do the asymptote first. I know my asymptote is of the parent function was this one right here. Okay, this purple ruler has to move based on what it said. Okay, so it said to move left 3 units, so this has to move left 1, 2, 3 units. Then it says go down 2 units. Well, if I move my ruler down, it doesn't really affect anything with my graph. Okay, so like going back over here, when my graph was originally here at the 0, it's kind of off the page, but when the graph was over here at 0, when it said to go 4 units to the right, 1, 2, 3, 4, it didn't change my horizontal axis. What changed it is when I said go up 1 unit. So that's when it changed, okay? So here, I had to go over 3 units from the 0. Originally it was here at 0. So I had to go 1, 2, 3. So right here at the 3, I am going to draw a dashed line to depict the new horizontal asymptote. Okay, let me go a little bit further down. Okay. And so I know that my graph, when I finish connecting it, it's going to get awfully close to the asymptote. Okay. Let me shift my graph a little bit down so you can see what happened. Okay. So notice how it gets really, really, really close to the asymptote but doesn't touch. Okay? The domain, anything to the right, don't put the equal to, right? X to the right of -3. The range is still going to be all real numbers like the parent graph, and this time the asymptote is not at 0, but at x equals -3. And that's it. That's how you graph exponential and logarithmic functions. Hope this helps. Good night.